We continue with the course Sustainable Energy and Green AI. And this is second part of the lecture focuses on the technical and operational aspects of IoT data collection and management in sustainable energy systems. In our previous part of the lecture, we explored how IoT serves as a foundation for AI in sustainable energy systems. We saw that IoT devices like smart meters and environmental sensors enable AI by providing real-time, contextual data from the physical world. This data is essential for making intelligent decisions about energy usage, predicting demand, and optimizing performance. In short, IoT is the nervous system that feeds the brain of AI. Today, we are going to step further. We will look at how IoT actually collects and manages this data, technically and operationally, and why that process is critical for building scalable, efficient, and sustainable energy solutions powered by green AI. Now that we have seen why IoT is essential for sustainable energy systems, let's look at the technical architecture that makes it work in smart buildings. At the base, we have a perception layer. This is where sensors live, measuring energy consumption, temperature, humidity, and even CO2 levels. These devices are the eyes and ears of the system, continuously collecting real-time data. Next is the network layer, which moves that data from sensor to processing units. In buildings, this can include wired protocols like BACnet or Modbus for building automation, and wireless options like Zigbee or LoRaWAN for low-power wide area coverage. Above that, we have edge or fog layer. This is where local gateways or controllers perform local analytics and filtering before sending data to the cloud. Why? Because processing some data locally reduces latency, saves bandwidth, and improves energy efficiency. Finally, the cloud layer. This where the large-scale storage and advanced analytic happen. AI models run here to optimize heating, ventilation, and air conditioning systems, HVAC systems, predict energy demand, and integrate renewable sources. The diagram on the slide shows how these layers work together, from sensors in the building to AI-driven decision-making in the cloud, creating a smart, energy-efficient ecosystem. Before we talk about how the data flows, let's take a closer look at the sensors themselves, the devices that make IoT possible in smart buildings. First, we have energy meters. These measure electricity, water, and gas usage at different points in the building. They provide the baseline data for energy optimization and cost tracking. Historically, these meters reported data once an hour. Then more advanced systems started sending updates every 15 minutes. Today, some applications like NILM or non-intrusive load monitoring require data every second to disaggregate appliance level usage. So the sampling rate really depends on the inertia of the process. Low changing or slow changing systems like water flow can be sampled less frequently, while fast changing electrical loads need a high frequency data. Next are environmental systems. These monitor temperature, humidity, and CO2 levels. This data is critical for maintaining indoor air quality and ensuring heating, ventilation, and air conditioning systems operate efficiently. Then we have occupancy sensors. These can be simple PIRs, motion detectors, or more advanced camera-based systems. They help the building adapt energy use to real-time occupancy, turning off lights or adjusting HVAC when spaces are empty. Another important group is HVAC performance sensors. These measure airflow pressure and sometimes valve positions. They allow predictive maintenance and ensure heating and cooling systems can run at peak efficiency. Finally, consider data frequency. Some sensors send data in real time, like occupancy or temperature sensors, while others report periodically, such as utility meters. Balancing these frequencies is a key to reducing network load and energy consumption. Together, this sensor ecosystem creates rich data foundation for AI-driven energy optimization in smart buildings. Now that we know what sensors we have, the next question is how do they talk to each other and to the cloud? That's where communication protocols come in. At the application level, or layer, we often use lightweight protocols like MQTT, which is ideal for low bandwidth IoT devices. There is also CoAP designed for constrained environments, and HTTP, which is common in web based integrations. MQTT is ideal for streaming sensors data to a central broker for many subscribers, perfect for energy monitoring and smart building dashboards. CoAP is better for lightweight, RESTful integrations, like querying a sensor or sending a control command. For building automation, traditional protocols still play a big role. BACnet is the backbone for HVAC and lighting control. Modbus is widely used for energy meters and industrial equipment. And KNX is common for lighting, shading, and comfort systems in smart buildings. These protocols ensure interoperability between devices from different vendors. When it comes to connectivity, we have three main categories. Short range options like Zigbee or Bluetooth Low Energy are great for in building sensor networks. For long range, low power needs, think large campuses or distributed assets, we use LoRaWAN or narrowband IoT. And for high bandwidth application such as video analytics or firmware updates, we rely on Wi-Fi or even 5G. Choosing the right protocol depends on the factors like data volume, latency, requirements, and energy constraints. In practice, most smart buildings use a mix of these technologies to balance performance and efficiency. Now let's talk about edge and fog computing, why it matters and how it supports sustainability. In traditional IoT setup, all data goes straight to the cloud, but that can create latency, high bandwidth costs, and even extra energy consumption. For smart buildings, there are thousands of sensors generate continuous data. This is not an efficient. That's where edge and fog computing come in. Both bring processing closer to the data source, but at different levels. Edge computing happens right at the device or gateway, literally at the edge of the network. For example, a smart HVAC controller analyzing temperature data locally. Fog computing sits one step higher on local servers or nodes within the building or campus. It aggregates data from multiple edge devices and can run more complex analytics before sending summarized information to the cloud. Why does it matter? Because local processing reduces latency, so actions like adjusting HVAC happen instantly. It also cuts bandwidth, since only relevant or aggregated data goes upstream. And it saves energy because less data transfer means lower network and cloud loads. Typical tasks at the edge include data filtering and compression so we don't send raw noisy data, local anomaly detections, for example, spotting a failing HVAC component before it causes energy waste. From green AI perspective, Edge computing allows us run lightweight AI models locally, avoiding the energy cost of cloud inference. This means smarter decisions with a smaller carbon footprint. In short, edge and fog computing make IoT system faster, more efficient, and more sustainable. Key goals of green buildings. Now what we have covered how data is collected and transmitted, let's talk about what happens next. Data management. This is one of the most challenging parts of IoT in smart buildings. First, the challenges. We deal with heterogeneous data formats. Different sensors and systems speak different languages. Then there is a high volume and velocity of data. Thousands of sensors can generate gigabytes of data daily, and much of it's time sensitive. So, how do we make sense of it all? What's their semantics tagging comes in. Standards like Project Haystack or the BRICS schema helps us bring order to this complexity. Haystack focuses on lightweight practical tagging for individual data points. So instead of just sensor 123, we know it's supply air temperature sensor on floor 2. Brick, on the other hand, provides more formal structure for modeling, relationship between spaces, equipment, and systems, ideal for digital twins and advanced analytics. Finally, interoperability. We use protocols like OPC UA, which act as a universal translator between different systems and vendors. This ensures that data flows smoothly from sensors to analytics platform, regardless of the underlying hardware. In short, good data management is what turns raw sensor readings into actionable intelligence. And without it, even the best AI models can deliver sustainable outcomes. Then we talk about IoT in smart buildings. The technology sounds impressive, but the reality is that day-to-day operation come with significant challenges. First, device calibration and maintenance. Sensor drift over time, and if they are not calibrated, the data become unreliable. That means that bad analytics and poor decisions. Next, firmware updates. With thousands of devices, manual updates are impossible. That's why over-the-air OTA updates are critical. But they also introduce risk if not managed securely. Speaking of security, cybersecurity is the major concern. They are dealing with distributed devices, often on shared network. Implementing TLC encryption, VPN tunnels, and zero trust architecture is essential to protect against attacks. Finally, the energy footprint. IoT devices may be small, but at scale, their power consumption adds up. Optimizing energy use through low power models and efficient communication protocols is key for sustainability. In short, operational challenges aren't just technical, they impact cost, security, and sustainability. Addressing them is what makes IoT truly viable in smart buildings. Now let's talk about how AI is applied to make building energy sustainable from technical perspective. First, predictive HVAC control is a key application. Using algorithms like model predictive control and reinforcement learning, HVAC system adjust heating, cooling, and ventilation dynamically based on real-time occupancy and weather forecasts. This significantly reduces energy waste while maintaining comfort. Next, energy demand forecasting relies on machine learning models such as LSTM networks and gradient boosted trees to predict load patterns. These forecasts enable strategies like load shifting and peak shaving, which lower both energy costs and carbon footprint. Finally, fault detection and diagnostics, combined with predictive maintenance, ensures system reliability and efficiency. AI models like autoencoders and isolation forests detect anomalies early, while predictive maintenance algorithms estimate the remaining useful life of components. This prevents failures, reduces downtime, and avoids energy losses caused by inefficient equipment. In short, AI enables smarter control, accurate forecasting, and proactive maintenance, key pillars for energy sustainable buildings. Let's look at the technical enablers that make AI-driven sustainability possible in smart buildings. There are three key areas: Edge AI deployment, model optimization, and carbon-aware scheduling. Edge AI deployment. Instead of sending all data to the cloud, we process it locally on devices like NVIDIA Jetson or ARM-based processors. This reduces latency, saves bandwidth, and lowers the energy footprint of cloud computing. Frameworks like TensorFlow Lite and ONNX Runtime makes it possible to run optimized AI models on these edge devices efficiently. Next, model optimization. Large AI models can be computationally expensive, so we apply techniques like quantization, which reduces precision from 32 bits to 8 bit. Pruning, which removes unnecessary connections, and knowledge distillation, where the smaller model learns from the larger one. These methods cut energy consumption significantly while maintaining accuracy. And finally, carbon aware scheduling. This means aligning energy intensive tasks with periods where the grid has the more renewable energy available. By integrating with grid carbon intensity APIs, we can dynamically schedule tasks like batch analytics or model retraining during low carbon periods, reducing the overall environmental impact. Together, these enablers ensure that AI in buildings is not only smart but also sustainable. To conclude, we showed how IoT enables data collection and management in energy sustainable buildings, from sensors and communication protocols to edge and cloud computing, while addressing challenges like interoperability, security, and energy footprint. We also introduced key sustainability enablers such as HAI, model optimization, and carbon aware scheduling. This is important because reliable real time data is the foundation of intelligent decision making. In the final part of the lecture, we will see how this data is used by AI models for prediction, control, and maintenance, while ensuring the AI itself remains sustainable.